Hello and welcome. In this tutorial, you will learn how to use MVTec HALCON to acquire images from line scan cameras. If you are not yet familiar with the concept of line scan cameras, we recommend that you watch the video Introduction to Line Scan Cameras first. After this tutorial, you will be able to acquire images from a line scan camera setup like this. This setup consists of a line scan camera, a slide which will be used to move the Do Not Switch sign to be inspected back and forth, a rotary encoder, a photoelectric sensor, and a special light for line scan applications to ensure optimal lighting. This tutorial will cover the following steps: connecting the line scan camera, aligning the line scan camera, adjusting the focus, configuring a photoelectric sensor as frame start trigger, configuring an encoder as line start trigger, adapting the trigger frequency of the line acquisition, and finally, shading correction. We start by connecting to our camera. For this, we open the Acquisition Assistant. Inside the Acquisition Assistant, we first must select the right interface for our camera. Pressing the Auto Detect Interfaces button will list all interfaces where a suitable acquisition device is connected. In this setup, we use a GigE Vision line scan camera. Select the GigE Vision interface. If you cannot find the correct interface for your camera, please check if you got the corresponding drivers installed. In some cases, you may need to configure the camera first. With the correct interface selected, we switch to the tab Connection, where we can connect to our camera. Once again, HDevelop is offering a detect feature, which will show you every camera available through the selected interface. Your camera should be selectable through this menu. If this is not the case, check if your camera is used elsewhere. Connect to your camera via the Connect button. To test our connection, we press the Snap button to acquire a single image. Next, we move to the Parameters tab to prepare the alignment of our camera. Please note, depending on the camera and interface, parameter naming conventions may differ. We want to adapt the image height. If the image height is too low, it makes seeing adjustments to the camera more difficult. If it is too high, the frame rate might suffer, which also makes adjusting the camera more difficult. In this specific case, a value of 500 is suitable. After adapting the image height, we press the Live button to start a continuous image acquisition. We can now start to adjust the camera position. For this, move the object to be inspected under the light source. This, of course, requires that the light source is already aligned with the path of the object. Start moving the camera and look to capture the illuminated part of the object. If your setup is correctly configured, you should be able to adjust the camera in a way that all pixels are capturing light homogeneously. At this point, the image appears overexposed. You can easily check for overexposure using the gray histogram by enabling visual output and setting both the minimum and maximum threshold to 255. As our image is heavily overexposed, and it is desirable for line scan applications to have the shortest exposure time possible, we lower the exposure time to 2 microseconds. Now the captured image is no longer overexposed, but it is also not using the full range of gray values. To correct this, we also set the gain to 2000. Now the full range of gray values is used, as you can see in the gray histogram. Alternatively, you can increase the exposure time. In this case, we have chosen to increase the gain to show the effect of both parameters on the captured images. A higher gain results in more noise in the image. A higher exposure time results in a lower frame rate. If your application allows it, it is recommended to increase the exposure time before increasing the gain. With a nav-aligned camera, we can adjust our focus. Note that you will only be able to focus your camera if your setup considers the working distance of your camera and lens. In some cases, you can use the object to be inspected. In this case, our Do Not Switch sign to focus your camera. The object used to focus the camera needs a contrast that can be used to judge the sharpness of the image. In our case, the print on the object is sufficient. We try to get this transition as sharp as possible by adapting the focus of our camera. Before we start the image acquisition, we set the image height to the highest value that will not negatively affect our application. Capturing more lines allows us to better judge the quality of the acquired images. In our case, we can set the image height to the camera's maximum height of 12,288 lines without negatively affecting our application. It is generally recommended to use an encoder in most line scan applications to be able to bring vertical distortions under control. In our application, due to its short run distance, the slide is continuously accelerating and decelerating. This makes the use of an encoder a necessity. Further than just synchronizing the line acquisition speed to the movement speed of the object, the encoder is needed to tell in which direction the object is moving, because only one movement direction will produce correct images. The photoelectric sensor is needed to trigger the frame start, when exactly the camera should start to acquire lines. In other words, it ensures that the camera is capturing an image while the object is passing under it. We begin the configuration of our triggers with the photoelectric sensor. For this, we will use the Image Acquisition Assistant. As we are now moving to triggered image acquisition, it is recommended to uncheck Update Image. Otherwise, it will make the Image Acquisition Assistant more difficult to use. The parameters we are looking for are Trigger Selector, Trigger Mode, and Trigger Source. Trigger Selector selects the type of trigger to configure. Trigger Mode and Trigger Source are then set for the selected trigger. We set Trigger Selector to Frame Start and Trigger Source to Line 3. Keep in mind that Line 1, 2, 3, etc. are corresponding to the I/O channels used to connect the trigger to your camera. Then we set Trigger Mode to On. Now let us run our setup with only the photoelectric sensor configured. As you can see, the camera is capturing images in both movement directions. In one direction, the images are capturing part of the sign with a wrong resolution in my direction. The images captured from the other direction also show only part of the sign, which is on top mirrored horizontally. So we want to synchronize the speed of the line acquisition and exclude the backwards movement from our image acquisition. For this, we use an encoder. For the configuration of the encoder, we will also use the Image Acquisition Assistant. Again, we are looking for Trigger Selector, Trigger Mode, and Trigger Source. We set Trigger Selector to Line Start. We've connected the signal A of the encoder to line 1 of the camera and the signal B to line 2. So we could set either line 1 or line 2 as trigger source to synchronize the line acquisition to the movement of the object. This, however, will not exclude the backwards movement from the image acquisition. To exclude the backwards movement from the image acquisition, we must use both signals of the encoder as trigger source. So we set trigger source to shaft encoder module out. And we set trigger mode to on. The shaft encoder module allows us to use both line 1 and line 2 to determine in which direction the slide is moving. Line 1 and line 2 are set to phase A or phase B, depending on which direction should be defined as forward. To be sure, whether line 1 or line 2 should be phase A or phase B, you can connect an oscilloscope with at least 2 inputs to line 1 and line 2 and visualize them simultaneously. Based on the phase shift from phase A to phase B, the shaft encoder module can tell in which direction the part is moving. If phase B is 90 degrees behind phase A, it is a forward motion. If phase A is 90 degrees behind phase B, it is a backward motion. In our case, line 1 is 90 degrees behind line 2. So, for this setup, we set phase A to line 2 and phase B to line 1. Now let us configure the shaft encoder module. We search the parameters using shaft and change the visibility from beginner to guru. For this, we need the parameters shaft encoder module counter mode, shaft encoder module line selector, shaft encoder module line source, and shaft encoder module mode. Shaft encoder module line selector is comparable to trigger selector. We set shaft encoder module counter mode to follow direction, shaft encoder module line selector to phase A, and shaft encoder module line source to line 2. We'd also set shaft encoder module mode to forward only, to only trigger in the forward motion. Then we set Shaft Encoder Module Line Selector to Phase B and Shaft Encoder Module Line Source to Line 1. The next step is to adapt the trigger frequency of the line acquisition. We learned in the previous part of this series that in order to obtain an ideal 2D image and avoid distortion, the resolution in pixels per millimeter should be identical in both the X and Y directions. Looking at the image, which should contain a perfect circle, we can clearly see that this is not the case in the images we have taken so far. To solve this problem, we need to adjust the frequency of the line acquisition. In the case of this camera, this is done by the frequency converter. In order to use the frequency converter, we need to calculate the ratio between the resolution in the X direction and the resolution in the Y direction. To do this, we can measure the radii of the ellipse displayed, for example using the Measure Assistant. The ratio of the two radii is the same as the ratio of the resolution in the X and Y directions. In this case, the ratio is 6.5. In other words, the pixel resolution per millimeter in the Y direction is 6.5 times higher than the pixel resolution per millimeter in the X direction. Since we are using the shaft encoder module as line trigger and the shaft encoder utilizes 2 pulses at a time, we need to multiply this value by a factor of 2. So, we set frequency converter input source to shaft encoder module out, frequency converter pre-divider to 13. And for our line start trigger, we set the source to frequency converter. Let us run our setup in script. The circle on the sign is now also a circle on the acquired image. However, we now acquired too many lines. In our case, an image height of 2,454 pixels is enough. The images are now captured only in the forward direction and are not distorted anymore. Since the images we've captured so far are very unevenly lit, the last thing we need to do is shading correction. This consists of a gain and offset shading correction. We won't go into the technical details of shading correction in this video. You can think of it as calibrating the light sensitivity of the sensor's pixels. Let us start with offset shading correction. We begin by filtering the shading parameters. For offset shading correction, we need a completely dark live image, which is best achieved by using a lens cover. We start with our live image. Under Shading Selector, Offset Shading is already selected. We set Shading Set Create to once and enable our offset shading correction by setting Shading Enable to 1. For the gain shading correction, the workflow is the same, except that we need to capture a live image of a completely white surface. This can be done with a white paper, for example. To avoid a faulty gain correction, the object must be moving. We set Shading Selector to Gain Shading, Shading Set Create to once, and enable our gain shading correction by setting Shading Enable to 1. With the shading correction applied, we have transformed our captured image into a more evenly lit image. This concludes this tutorial. You now know the basics to configure and set up a line scan camera with MVTec HALCON. The next step could be to calibrate your setup using one of MVTec's calibration plates. Thank you for watching.